This will be the laboratory 11 and 12 setup and background video on frog nerve and muscle. We'll look at the overview, some dissection notes, and then the equipment setup and calibration. These are two classical experiments with frog nerve and frog muscle, and we'll look at various aspects of action potentials and muscle contractions in the frog. So Lab 11 is sort of the setup, get familiarized with the equipment and kind of get volunteers and people figuring out who's going to do what. We're going to be using the American bullfrog as a experimental subject. Their conservation status is least concerned, and in fact, in some places, the American bullfrog is considered an invasive species. So we'll have the bullfrogs that are actually raised in a laboratory for scientific purpose for use in the lab. They tend to be fairly big, and part of the reason why we like them a little bigger is it's easier to dissect out the sciatic nerve, and we get a nicer chunk, and there's less likelihood that it's damaged during the dissection. So you should know the general procedures for what we're doing at the beginning of the data collection, but not all the little nitty-gritty details per se. And we'll try to really emphasize the important aspects of the experiment. So first of all, we use the amphibians for this experiment. A bullfrog is certainly one of those, is because they're what they call diadermic breathers. What that means, you can see it right here, diadermic breathers. What it means is that they respire across their skin, and there's enough oxygen that gets across to supply the oxygen for metabolism and things like that, even though they're going to be brain dead. And to make them brain dead, the frog is going to be what we call double pithed. So pith is a nice way to say destroy the central nervous system. The double pith means we destroy the brain and the spinal cord. Technically, they're dead. In our society, the cessation of brainwave activity is generally the definition of death. But because of the diadermic breathing, they still have metabolism, so we can still get a muscle twitch. So it works out very nicely for that purpose. The key component is they can't feel pain. When the brain is destroyed, they can't interpret anything, and the spinal cord is destroyed. It reduces the chance, and if you do it right, eliminates the chance of any reflex response. So it works out pretty well. To dissect the frog, the first thing we want to get the sciatic nerve. Now, when you have the skin of the frog, you want to completely remove it and get it out of the way. All amphibians produce neurotoxins in their skin. You're probably familiar with the colorful frogs from the Amazon basin that have very strong poisons and things in them, or maybe what they call cane toads, and you see those in Pacific Islands and all the way to Australia, where people lick the backs of them and get high from it. So there are neurotoxins in a bullfrog, and it's just not unsafe to us. But if you touch the sciatic nerve to it, it would destroy the sciatic nerve. We're trying to be able to measure the action potential on it, so we don't want to damage it from the neurotoxin. So it's best just to remove the skin, as you see in this picture here. And then the sciatic nerve, very similar to us. It exits the spinal cord, right, towards the lower part of the spinal cord, goes across the thigh, and then splits into what the tibial and the peroneal branches. So we want to be able to get the sciatic nerve from the knee to the hip. Now this is not a big frog. You can kind of see, relatively speaking, in terms of how big this person's hands are. And like I said, we get bigger frogs, so you don't have to worry about the dissection across the hip and up into the small of the back. If we have a large enough frog, we can just get the sciatic nerve part from the thigh, and we'll be fine. What you can see here is they're using glass electrodes, and they're trying not to touch the nerve and depolarize it. The nerve is running right here. This is the back, and you can see the thigh right here. So right here's a good picture of the nerve all the way down. And they've isolated it without stretching it too much with the glass rods. Again, this last part from the hip to the back, that takes a significant amount of time. And if you have a big enough frog, then you can just do it from the hip to the knee and get the sciatic nerve from there. You want to be gentle and not stretch it. If you stretch it too much, you can damage it. Or stretch it enough, you'll completely damage it. It won't conduct any action potentials anymore. And so what you do then is you just literally snip it out of the leg. And then you're going to put it in a nerve chamber. I'll show you what that looks like in a minute. When you're done with that, you're going to isolate the gastrocnemius. So that's the calf muscle. And this isn't a great picture. One, they've used twine. We use thread. And what they've done is they've isolated it from the lower part of the leg and then cut the Achilles tendon that goes underneath the foot. And then you tie the thread onto the Achilles tendon. Some people remove the entire gastrocnemius. We like to leave it in place because it allows you to easily stabilize the leg so it doesn't move. When you cut off the whole gastrocnemius, it's hard to stabilize that lower portion. And oftentimes when people do, they end up removing the part of the leg anyway. So it just works best if you leave it attached at the upper part, so the proximal end, cut the distal end, and then use pins to hold the leg down. So when it contracts, it doesn't move the leg up. What you do is you will put right here in the middle of the muscle belly these pin electrodes. They're called pin electrodes because they look like pins. And then you would send the shock to those that would contract, and we'd be able to measure the strength of contraction. We're not going to worry about it in this video, but we'd also play with the heart. And this is live video from somebody with the experiment in lab. You can see the heart beating, and it's kind of neat to do that and things like that. But since I'm not holding you responsible for the frog heart information on the laboratory exam, we won't worry about it for this video. So while a couple people are getting the sciatic nerve dissected out and isolating the gastrocnemius, the other members of the group will be setting up the recording devices. So we have the biopack here. We have a stimulator here. We have cables coming off the stimulator that we'll be able to shock the nerve with, basically. And then off the biopack MP30, this is that analog to digital board. We have recording electrodes. That's what the R is. So we have a negative and a positive recording electrode. We have a ground. We have a negative and positive stimulating electrode. Can't see it, but the stimulator has a little window that allows us to dial in any stimulus we want from literally, 0.01 to 10 volts. To actually go to 100 volts. It's got a little key thing that you could change it if you wanted to go even higher, but once you get above 10, it starts to get dangerous, so we leave that locked. What you can see here is here's a nerve chamber. In the nerve chamber, you see the sciatic nerve right here, and then you see the various stimulating and recording electrodes. here. So these are the stimulating electrodes down here. These are the recording electrodes right here. And theoretically, you'll be able to shock the nerve with the stimulator. That would set up an action potential. Technically, it's called a compound action potential in the sciatic nerve. That would send the action potentials that way. We record them on the other end. Okay. So again, we're not going to worry about the setup. As a matter of fact, like I said, some of the people in your group would be doing the dissection. Some of the people in your group would be setting up for the data collection. And one portion of the lab would be collecting data on the frog nerve, and the other portion of the lab would be collecting data on the frog muscle. And then theoretically, in a perfect world, you just switch spaces and go to the other group's setup, and then collect data off their setup. So there's, not quite, but 1/3 of the lab will do one part and the other 2/3 won't. So it'd be unfair to ask you about the setup of something you haven't done, or the nitty-gritty details of the dissection when you haven't even done that part. So again, here's our setup, and you put the frog nerve in the chamber, and what you would do is you would set it up so that, I'm going to go backwards, set it up so the stimulator automatically triggers the recording of the BioPack machine. The problem with the way the action potential is set up, it's not really a problem, but it's, a reality that we have to deal with, is it happens very quickly. Okay. Now, if you look here, it's hard to see the exact numbers. All right. But these are in milliseconds, right? And so this is 5 milliseconds here, roughly. Here's 5 milliseconds here. Here's about 5 milliseconds here, not quite. So this whole thing is 20 milliseconds, so 20,000th of a second. And the action potential is just this little spot here, just a couple milliseconds long that we see. And so if you didn't have the machine automatically record the things for you, by the time you hit shock the nerve and then went to record it, the event would be over. So we have to set it up automatically to do that. On this recording, and sometimes they're a little different, people sometimes switch the top and bottom one. This upper one is the stimulus, and the bottom one is the response. Now, see the little zigzag here initially? That's called the stimulus artifact. We're actually recording the stimulus itself, so that's not the response we're looking for. But if you look, you see this little kind of zigzag line here, so it goes up and then back down. That's called the compound action potential. That's the response that we're looking at. And we will set the stimulator at different levels, make sure it worked, and then we would start at a fairly low level, increment the stimulator up and giving it a single shock each time, record where we first saw a response. That's called the threshold voltage. Keep on shocking it in increments until it would get bigger, bigger, bigger. And then we do that until we shock it and it doesn't get any bigger. That's called the maximal voltage. The maximal voltage is the largest voltage above which the response doesn't get any bigger. So it's kind of what we do, and we'll look more at it in a little more detail later. The frog muscle setup is a little bit similar. We actually have a little better stimulator than what's shown here. It's got a set of this little dial. It's got an LED dial, so you can get it, pretty exact what number you want. Here's the stimulator. There's slightly different electrodes. If you look at the electrodes here, they are built to go in these little fittings on the side of what's called the nerve chamber. Here, it's hard to see, but these are called pin electrodes, and the idea is these go directly into the frog muscle. Okay. But other than that, this part, the stimulator, the MP30, very similar. And then the other thing is we have what's called a force transducer. And basically what you do is you tie up the frog muscle to one of these little eyelets, stimulate it, the muscle contracts, it pulls on an eyelet, and that allows us to record it onto the computer. Okay, so we're going to measure the force of contractions and the number of contractions in frog muscle from our various stimulating parameters. So, you do have to do a couple other things for this one. We do tie a 50-gram weight on it to calibrate it. The top line is the stimulus line. It's hard to see, but notice where there's a stimulus, there's a little triangle. The triangles aren't always a stimulus. They're called event markers, and they could represent any event. But this is set up to have, every time you have a stimulus, you see an event marker. If you hit actually F9 on the computer, F12 on the computer, there's a couple other Fs that will do it as well. You can insert an event marker. So sometimes you see a random one, but in this data, every time you see a little triangle, that means we gave a shock to the muscle. Okay. Now, this is from a better computer that is saving the data at a higher rate, that has higher memory than we have in our laboratory. And the problem is you have to sample this really, really fast, and it takes a lot of computer-powered memory because we're doing it continuously. So we're not going to use the top part as our indication of what the stimulus is. We're just going to use the LED readout from the stimulator itself. Okay, and the bottom part is our response. We're giving it a single shock here. So all these are single shocks. And notice we don't see a response for the first two. And we see a small response and it gets bigger. And then after this response, it doesn't get any bigger. We'll explain what those are, what threshold, maximal, subthreshold, submaximal, supramaximal, all of those things are in the next video. But we're going to be able to look at different responses. Then what we're going to do is we're going to set it to the maximal voltage, so the stimulus voltage that gave us the biggest response. And then instead of giving it one shock, we're going to give it multiple shocks and then increase the frequency. And we're going to have what's called temporal summation from doing that. So for the frog sciatic nerve, right, we're going to set up and calibrate according to the supplement. And for the skeletal muscle in the frog, we're going to set up and calibrate according to the supplement as well. Now, just a little background on the frog. The idea is we're going to have a stimulus that's going to go over these recordings here, these electrodes. And if the stimulus is big enough to open double-gated sodium channels in the axon of a neuron, it will generate an action potential. Okay. Now, a couple background things that are probably good to mention that you may or not remember from your anatomy experience. This is a sciatic nerve. You probably didn't learn this, and some graduate student years ago with not much time on his hands. I guess too much time on his hands, probably a better way to say it. Took a whole bunch of sciatic nerves from frogs, stained them, made cross-section, threw them to the microscope, and counted all of the axons. And he found about 1,500 per sciatic nerve. So there's 1,500 axons in a nerve, in this nerve particularly. Right? So remember, a nerve is a bundle of axons in the peripheral nervous system. Okay, so a bundle of axons in the peripheral nervous system. So what we're looking at is we're not looking at the individual action potentials of each axon. We're looking at the cumulative sum of those, and this is called the compound action potential. Now, in grammar school, you might have learned things like compound words like schoolhouse or bookkeeper. So it's made up of a compound word of two or more other words, right? Or raccoon nook keeper, which is the most consecutive double letters in the English language for a word. But when we stimulate the sciatic nerve, we're trying to stimulate each individual axon to reach threshold and fire and action potential. Now we'll learn in lecture, so might as well discuss a little bit now, that the threshold for that is about minus 55 millivolts. So we have to get the neuron, in this case the axons, because we're looking at the sciatic nerve, to reach a voltage of minus 55 millivolts. And the way we do that is we give an electrical shock. And the bigger the electrical shock, the more likely that axon is going to reach threshold and fire an action potential. And what we're doing, because we're recording externally, we're recording what's called a compound action potential, which is the sum of all the action potentials within the neuron. So when we look at the compound action potential, right, we see here's my stimulus artifact, and then the little mountain with the valley. That is my compound action potential. It's a very nice compound action potential. It's actually biphasic because of the way they set up their recording electrodes. It sets up for a biphasic response. We set ours up a little differently, and we don't see typically a biphasic response because we put the one electrode in a different spot, and so we don't see a biphasic response. But that's fine. We like the recording we get, and sometimes easier to deal with. So once you get this, you could go ahead and highlight the action potential, and when you do that, since it's the blue recording, not the red, you would change this to a blue P to P, and whatever voltage it read in the P to P setting, just like this. What the computer does is it takes the highest point and the lowest point in the highlighted area, does the math, and displays it there. So we can see how big that action potential actually gets. Okay? And again, it's called the compound action potential because we're looking at the sum total of the entire response of the nerve. So here's some examples of sample data. So what happened for this is we decided, okay, what we're going to do is we're going to record the stimulus voltage and record whatever response we get in terms of the compound action potential, right? And so we started at 0.1 volts and we didn't see any response. So the amplitude was 0. At 0.2 volts, we saw a small response, 0.0029. At 0.3, it doubled to 0.0058. At 0.4, it got bigger. 0.5, it got bigger, but we don't have it recorded here on the table. 0.6, it got bigger. 0.7 and 8, it got bigger. 0.9, it got bigger. But then we went bigger than 0.9, it gave us the same response. So each one of these intervals theoretically has a specific attribute that we can look at in terms of relative height. Okay? So the two most important points to understand, because everything comes from those 2 points, are threshold and maximal. So our threshold voltage is the smallest voltage that elicits a response. So at 0.2 volts, that's where we first saw a response. So that's my threshold voltage. By definition, anything less than 0.2 is considered subthreshold. So if I gave the nerve 0.1 volt stimulus, it wouldn't fire. If I gave it 0.19 stimulus, it wouldn't fire theoretically because we said 0.2 was threshold and anything below that is subthreshold. If I gave the stimulus a 0.199999999, it still theoretically is subthreshold and should not fire. Now, realistically, it probably would, but we're not going to fine tune it that much. So once you've established a threshold number, anything below that, by definition, gives you no response. The other one we need is maximal. And maximal response is the voltage above which the response does not get any larger. So you don't see an increase in the response after that voltage. And that's at 0.9 volts for our experiment here. Notice the response was 0.0133, and then notice anything above 0.9 gave us the same response. What this really is data for is spatial summation. As we increase the stimulus voltage, right? So here's the stimulus voltage in this first column. As we increase it, we're getting more and more active units in the nerve itself. So more and more axons are reaching threshold, generating action potentials, and we can see that display in terms of the compound action potential response. So that's called spatial summation. We're seeing an increase in the number of active units, and that's why we see an increase in the amplitude of the action potential. Now, one of the things that sometimes confuses students is we talk a lot about action potentials in class, in lecture, but the action potential we study in lecture is an individual action potential. It's an action potential that happens on an individual neuron on an individual axon. And we're measuring externally from a nerve which is made up of a whole bunch of individual axons. So we're not going to have the same voltage. It's not going to look the same. We're not measuring the same thing. To get the action potential to look like the one that we study in class is we have to measure intracellularly. We have to measure inside the axon versus outside to see the response that we're going to study and you should be familiar with in class. So sometimes that's confusing to students, and we try to say, okay, compound action potential, and then for the other one for this, we say individual action potential. But when we get into the lecture, we'll just say action potential. And like most of the time when people are talking about action potential, they're not talking about the compound action potential. They're talking about the individual action potential within an axon. So this is spatial summation because it's made up of the individual action potentials. Now remember, the individual action potentials, I sort of explained it. If they reach threshold, they fire. And if they fire the exact same way every time. Okay? So that's called all or none. So individual action potentials are all or none, meaning if you don't reach threshold, nothing happens. That's the none part. And if you reach threshold, the all part is they're going to reach the same height and do the same thing every time. Now the individual action potentials, the axons within the nerve, make up the compound action potential. And the compound action potential is what we call graded. And the reason why it's graded is in this, what we call the submaximal range, the range between threshold and maximal. Anytime we increase the stimulus, we get an increased response. So that's what graded means. The size of the stimulus determines the size of the response. So here's my graded response here, which really, we say it's graded, but technically it's graded between threshold and maximal. And the reason why it's not graded below threshold, that's the subthreshold area. And at the subthreshold area, we have not a big enough stimulus to elicit a response. We don't see anything. And above maximal, it's called supramaximal. Above maximal, we don't get any bigger because all the units are going to be recruited are already active, so you can't get any more than all. So it doesn't get any bigger. But in the submaximal range, right here between threshold and maximal, that's the graded part there. So that's sort of the compound action potential. Now for skeletal muscle, we're going to do the same thing initially. We're going to look at spatial summation, just like we saw spatial summation in the nerve a second ago. An increased response because of an increase in the number of active units is spatial summation. And when we say that, we mean the individual action potentials, more and more of them reach threshold, and that's why the compound action potential gets bigger. Well, we're not measuring the compound action potential in the skeletal muscle. We're actually measuring a muscle twitch. Muscle twitch doesn't look like this. It's an artifact of how fast the computer is moving when we collect the data. But each one of these little spikes are a muscle twitch. A muscle twitch is a single muscular response to a single stimulus. And as we increase the stimulus voltage, you see it going across here, right? We see an increase in the response, and we're going to have the exact same terminology we had. The smallest voltage that gives us a response is threshold. The maximal response above which we don't get any bigger, right? That would be the maximal. Anything above maximal is supramaximal. Anything below threshold is subthreshold, doesn't give us a response. And anything between threshold and maximal, right, is called submaximal, and that's the graded area. So we're going to look at the twitch tension. We'll study a little bit about the twitch itself as well. And that's very similar to what we talked about for the nerve. Okay? So it's spatial summation. So here's an example of what we could look at in terms of the skeletal muscle twitch. Okay, so this shows that below 0.4 stimulus voltage, there was no response. That's subthreshold. At 0.4, we got a muscle tension of 6 grams. So that would be our threshold. As we increased voltages, we got bigger and bigger responses until at 1.2, it was 72 grams change. And then above that, it didn't change, so that's maximal. So this is all the exact same information we had for the sciatic nerve, but now instead of measuring the compound action potential, we're measuring what's called the twitch tension. How much tension does the muscle twitch generate when it contracts? Okay, and that's, again, spatial summation. So a muscle twitch is a single muscle response to a single stimulus. So here's an example of a muscle twitch. Okay, might as well mention it now. A muscle twitch has 3 components to it. The initial component is called the latent period. The latent period is the time from the stimulus to the time when we actually start to develop strength in terms of the contraction. It's called the latent period. Latent means delayed. Like if someone has latent puberty, it means they have delayed puberty. So the latent period is the delayed time. It's not like nothing's happening in the latent period. What we're doing is we're stimulating the muscle fiber to basically reach its threshold. So very similar again to the axon. If we get it to reach threshold, then it sends an ax potential, and the ax potential leads to muscle contraction. Now, without getting into too much detail, you don't have to know this, but I just want you to understand that a lot of things are happening on the interior of the muscle that you can't see during the latent period, right? So if we give it a big enough shock to cause a muscle twitch, it's going to be made up of how many active fibers are contracting at the same time. So it's, again, similar to the compound ax potential, that it's a graded response that depends on the number of active units. So in the active units, what's going to happen is you're going to give it a big enough shock, and you're going to set up a muscle action potential, and we'll call the sarcolemma. That's the exterior covering of the muscle. So this right here is the sarcolemma. Now, this muscle doesn't show it in this picture, but muscle has in the sarcolemma these little invaginations that move into the interior of the muscle called transverse or T-tubules. And their job is to bring the electrical excitement into the interior of the muscle. And located along the transverse tubules are these special receptors called DHP or dihydropyridine receptors. And when these receptors get excited, they have a conformational change. They're actually hooked up to a calcium channel. It's a gate, so a calcium gate for a calcium channel. The calcium channel is located in the lateral sacs, or sometimes known as the terminal cisterns or terminal cisternae of the sarcoplasmic reticulum. Okay, so this is the smooth endoplasmic reticulum within muscle. And when that DHP receptor gets excited, it changes its shape. It has a conformational change. That opens the gate in the calcium channel. Calcium diffuses out down its gradient because it's a higher concentration inside the lateral sac where it's stored than outside the cell. When calcium diffuses out, it binds to a protein called troponin. Some people say troponin, but I say troponin. And what happens with troponin is troponin moves what's called tropomyosin, and that's an inhibitory protein that blocks actin-myosin interaction. So calcium allows that to move out of the way, and actin and myosin interact, and that's when we start to actually develop tension. So all that stuff I just said, you don't have to know, but that's what happens in the latent period. So it's not like nothing's happening. There's a lot of things happening. The second part of the muscle twitch is called the contraction period or contraction phase. That's when we develop tension. So when we start to develop tension up to the peak contraction, and not surprisingly, from the peak back down when we reach baseline, that's called the relaxation period. Now, depending on what type of skeletal muscle this is, it can fire very quickly within 10 milliseconds, and at other times it takes significantly longer to do that. Then, when we've established the twitch and looked at it a little bit, we're going to change the parameters of stimulation, and we're going to put the stimulus at maximum. And the reason why is at maximum stimulus, we're assuming that all muscle fibers are recruited. If all the muscle fibers are recruited, any change in activities not due to recruitment, because they're all controlled for already. We'll see in the frog skeletal muscle at higher levels of stimulation that's not true, but in humans it would be. But frog has a little extra muscle that humans really don't have much of. So we're going to change the frequency instead of giving it a single shock. So far, all of the data, whether it was a nerve or muscle, we're just talking about giving the muscle a single shock, just one, or the nerve just one. Okay, but now we're going to not change the voltage, we're going to change the frequency. So we're going to give it multiple shocks, so a volley of shocks, and we're going to increase the frequency and make it go faster, 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 and observe what happens because of that. Because each active unit is going to be doing more work, that's temporal summation. And so think for temporal summation, think frequency. For spatial summation, think recruitment. So in this case, we're changing the frequency, so that's going to be temporal summation. And for temporal summation, we're going to look at the different muscle responses for that. We're going to go from a twitch to what's called trepe, to what's called wave summation, and then eventually to what's called tetanus. Okay, so we'll explain those and what's happening with each one. But after twitch, all of these things are considered to be forms of temporal summation. So we'll talk about the three basic forms of temporal summation and what causes each in frog muscle in the next video.